Welcome to Func Prog Sweden. This is the ninth Func Prog Sweden this year. As always, we would like to thank all our recurring viewers and all our new viewers to the meetup. I will first go through the agenda today. So I'll do a short intro and then we will head over to Till and his presentation. Monads are everywhere. Maybe that's bad. And then the second presentation will be Introduction to F#, Web Programming with Web Sharper by Adam. And then in the end, I'll do a schedule and summary. First, I would like to thank our video sponsor, Adabeat. Adabeat is an IT consultancy company with offices in Stockholm and Ho Chi Minh in Vietnam. A lot of them are doing functional programming at Adabeat. And if you want to know more, check them out in social media or on their webpage, adabeat.com. I also want to push the schedule a bit. We've updated it now, so we have a ready schedule for the rest of the year and also for the first month next year. And later this month, we will be in real life at Funnel in central Stockholm. So if you are in Stockholm or if you're coming to Stockholm the 25th of October, please sign up. You can meet in person and you can also enjoy some free drinks and some free food at Funnel. Yes, and if you want to support the Func Prog Sweden community, which of course you want to do, you should head over to the meetup page and join the club. And you should of course go to the YouTube channel and subscribe. And if you really want to support the community, you head over to the spread shop and you get a t-shirt with the Func Prog Sweden logo on. Now you can see it. If you have questions during the presentation, please don't hesitate. Shoot them in the chat and I will read it up to Till and then later Adam. So, with that said, let's get started. I will head over to Till Schröder and his presentation. Monads are everywhere. Maybe that's bad.
Hi, I'm Till. I'm going to talk about effect systems, and we're going to start with monads. But first, I will start not by talking around it too much and just go into a practical example. Let's look into some code. You can maybe imagine this is JavaScript or some other C-like language. Let's say we have some email address in a string. I want to check if that is a good email address because we only want to allow email addresses, say, from .edu domains because we are only for students or something like this. We might want to get the domain from the email address, so everything after the @ Then we want to get the top-level domain of that domain. So in this case, that would be .red. Then we could check if that is a good top-level domain, which it is not. .red is very weird. So we would fail and the result would be false. There's an issue though, namely some of these functions could fail in theory, right? If we have domain from email address, that is a function that if the email address is malformed, in this case it's just a string, it could not include an @ could not include a domain, it could just fail. If that is the case, this code wouldn't work. So in this case, I wrapped it in a try-catch. So in theory, now all of these functions could throw something and we could catch it later on. But usually, exceptions aren't that well regarded. Especially functional programmers often have issues with exceptions. If you're looking at all of these functions, you can tell which of them is going to throw. And you're not going to know exactly what they can throw. And it makes some really confusing control flow. So if you only have one try-catch, that's fine. But in theory, if you throw an exception, it can jump up as many layers as you feel like in the function call stack. And that is pretty weird. Actually, in JavaScript, there's a second way of handling code that might fail, that is promises. It would make no sense, of course, to wrap this in promises, but we could try it out. It would work. I could just create a promise of my string that I start with, and then with .then, I could chain together several of these functions, which all then might fail. I would have to rewrite these functions, of course, to return a promise each from a string. But it could work. It's obviously somewhat of a weird hack, and I still can't tell which of these cannot fail, but I can kind of encode that this is a function that can fail. In fact, promises already do this. If you're in JavaScript, you see the async keyword, or that something returns a promise, you know already it might fail. So we might be able to create our own type where we encode that it might fail without being asynchronous. So in this case, I would want to be able to allow chaining with .then, .then, the same way as you would do with promises, without the asynchronous part of it. And we could add a new function called .map, just like an array.map, to modify the value without it being able to fail. So then I could have optional from my email address, and then I could do .then, domain from email address, .then, top-level domain from domain, and then .map to check if this is a good top-level domain. The map would signify that is good top-level domain can not fail, because, I mean, that kind of makes sense. If the input is malformed, you just return false. You don't need to return an error, because it's just not a good top-level domain. With this code, we can clearly see which parts can fail, which parts cannot fail that we have chained. That's a good part. What would happen if this failed? So if we had domain from email address, for example, the very first function that we're calling, just not have anything, it would just return nothing instead of a new value. And then the other two functions wouldn't even be evaluated. So I wouldn't have to call top-level domain from domain or is good top-level domain. We would just stop there and have no value. Which means we're kind of circumventing this, but unlike exceptions, I can't jump out super far. I'm only within this option chain do I basically skip the normal control flow. And we can actually implement this. Like, this isn't super advanced. Here I'm using TypeScript type annotations. If you don't like TypeScript, are not familiar with the type annotations, you can feel free to ignore it. Just meant to be help to those who do understand it. So I would just have an optional type, which is generic over my result. In this case, it's probably like a string or something where I'm processing the individual parts. I can construct it from that string or from whatever type T is. And then I have a function map and a function then. Then obviously takes a function that also returns an optional, since everything in a then block might fail, while map just takes a function that always succeeds and doesn't return an optional. I can actually implement this fully, so I'm not going to go into this in detail, but here's a complete implementation that works just fine, just to prove that there's no magic or anything. We can have a constructor, and that's the important part in TypeScript, where we have it's either a value or it is nothing, which is a symbol to declare that we don't have anything. You can cast this from some type. You can just create nothing, and then you can have map and then, and both basically follow the same flow. We just check, do we have nothing that we're operating right now? Then continue with nothing, just return nothing again. So the entire chain continues. If I do then several times, I will .map, I will do nothing when I start with nothing. The only difference between these two, of course, is that with map, I need to construct a new optional form from it. That's already like, I feel like this is better code than we had before in some ways, right? Because I can clearly see what fails and what doesn't fail. But it has a downside. I mean, I don't know how it failed exactly, and we can improve the structure. I can make a type that encodes also how it failed, meaning I can include an error message. So instead of just being optional, I'm making a type called result, which now is generic over two parameters, one of the value that I'm containing and one of an error type that I have if something goes wrong. That isn't too hard. It's basically the same. The type annotations look even more confusing, but it's basically the same stuff. I can cast it. I can just do from and construct a new value that works. I do from error, and then I immediately say that it fails. And I can do .map and .then again. Again, I can implement this, just a couple lines of code, no weird magic. And again, I just check, is this my error symbol? Then, we go on with an error. Is this not my error symbol? Then we call the function to continue the chain. And in practice, this would look almost the same. I do result from, and some error type, which obviously would need to be something that you define. And then domain from email address and top level from domain can return either a success value or error type, whatever that is, and map is simply successful. And then at the end, with my result that I have created, I can check, is this something that was successful, so a string that I've generated, or is this an error type and something went wrong, and I can check what actually went wrong in my error type. Maybe the error type is also a string, and I just describe, oh no, there's no domain, something like this. You can just put in an error. So that's pretty good. And in fact, this is kind of like a pattern, right? I just started with promises, and promises kind of sounded like a good idea. I made the optional, which looked pretty much like promises, and then I made the result type, which also looked kind of the same. It's overall the same structure, and we can reduce this down to a pattern. The same as like object-oriented patterns would work, like a visitor pattern or something, like steps that you can reproduce in your code to achieve a similar result. And the common parts is there's a function called .then, which allows me to chain things together that have an effect. And by effect, I here mean everything that skips out of the normal way of doing function calls. So usually I chain function call 1, function call 2, function call 3, but with this effect I can skip out of it and do something in between, or shuffle them around to do something interesting. Any kind of stepping away from just doing them in order, I call an effect. And with .then, I can signify a function that does an effect, and I can chain them together. And with .map, I can do something that doesn't do any effect, it just processes data normally. And of course, I need some kind of constructor to make this work, because otherwise I can't create values of this type. That's a pretty simple pattern, like simpler than most object-oriented patterns that we'd have to learn. The interesting part is this is what a monad is. If you do just this, just these three functions, and you apply them with a little bit of common sense and make them work, with just these three functions, you have a monad. So there's no more secret stuff. If you just do these three functions, implement them correctly, you have a monad. You can extract them into an interface, something like everything is a monad. If it looks like this, it's kind of pseudocode, but you know, you have I want to have a constructor, I want to have a map function, I want to have a then function. And then if you implement this interface, again with some common sense that actually makes something useful, you have a monad. And that's basically it. And you don't need to have this interface, right? We have already seen now 3 correct monads, which is result type, the optional type, and JavaScript promises, which are already there. Okay, but what does this semantically mean? Like, what am I actually expressing when I use a monad? And one interesting way to look at it is that we compare code that doesn't have monads to compare to code that does. So if we were to write some sequential code in a C-like language, we would just go, we would run a statement, then we write the next and so on. And I already say then, but it doesn't say then in the code. It says parentheses, semicolon, new line, parentheses, semicolon, new line between each statement. And I'm just replacing this with going .then, .then, and also some parentheses. If we're taking this structurally, that means what monads are for is to chain statements together. So statements are expressions that also have some kind of effect, usually in imperative languages. And monads are our feature of taking these things, these like small capsules of providing an effect, and chaining them together in an order. So chronologically, this comes first, this comes second, this comes third. And usually, this is the job of the semicolon. So like ever since Algol, the semicolon was the idea of chaining statements. You start with a statement. If you have a block of code, you have a list of statements. They're separated by semicolons. And that is what gives them order. And C has adopted this. Every modern language basically based on C. And then in Kern uses the semicolon as a way of chaining statements together into a given order. You can actually see this, interestingly enough, if you write C code where you have a function call that calls, where the 2 parameters are other function calls, separated by a comma, not a semicolon. The order in which these functional calls are called is undefined behavior. Because you need the semicolon to define order, right? Which is, that case, always in C except for for loops. For loops don't make sense. Anyways, monads are our way to overload the behavior of the semicolon operator, right? So the semicolon operator just says, do this, then do this, then do this. And we can do that with monads as well. But with monads, we can also inject new behavior, do something interesting. Our result type basically says, as soon as you find an error, Do not continue with the other things that expected you to have a success value. That's all we're doing. We are changing the way that we sequence statements together. Okay. Now, the first part of the title of this presentation was Monads are everywhere. And I feel like once you've listened to this, you can maybe think this is a little bit more plausible than when I started the presentation, because this is a pattern you might have seen before. And I want to give a quick rundown. For example, in JavaScript, right? We looked at promises, and they're also arrays. Arrays are also monads. They have a map method that works exactly like the kind of map we had here. And there is a flat map method, which does the same as the .then. In fact, if you don't believe me, think of an array that might have 0 values or 1 value exactly. Then, if you only limit yourself to these states, using .map and .flatmap works exactly the same as the optional type that I defined before, right? Using .map simply applies a function that takes that single element and works on it, and .then would then be a function, or flatmap would be a function that processes in some way which might result in the list becoming empty or continuing remaining 1. Meaning you have the same behavior as optional, just it could potentially be even more values. Which means arrays in JavaScript are also monads. You can look at C#. C# goes even further, with system.link being very much monadic, allowing you to basically have every numeral structure be a monad. And tasks, in a way that they are similar to promises, kind of are monadic as well. Rust is going mad with having monads everywhere, but never saying the word monad out loud. Error handling is kind of monadic. Optional values are kind of monadic. All kinds of like vectors and lists are monadic. The async await isn't really monadic, so the promise and futures they have, unlike JavaScript, aren't really monads. But the way you use them still works like a monadic effect, kind of. So they have monads everywhere. C++. The insanity is C++, obviously trying to have as little to do with monads as possible, does have a monad in the standard library with std optional, which works just like the optional type I laid out here, and that has the end-then method, which allows chaining just like then would do in my example. I think that's pretty interesting, and you can find in the standard library of most mainstream languages monads. And you can define monads in basically every language we currently use, except for like specific purpose languages. Maybe SQL you can't, but pretty much anywhere you can find monads. You can absolutely implement a monad in C. It wouldn't be generic, but you could, specify the types and it would work just fine. But how did we get here? Why are we in the state that there are monads everywhere, but nobody uses the term monads? So historically, there's actually a very interesting paper from 1965, which basically uses monads, also without using the term, because it wasn't really coined for this, to describe Algol. The first languages that uses semicolons to chain statements was mathematically described using monads, because semantically, monads are a way of describing semicolons. It makes sense. If the point of the paper was to describe Algol in the terms of lambda calculus, and to do this, obviously you can't have sequential statements in lambda calculus, really. They used a structure which is basically like monads. An interesting paper from 1994 points this out and says, Peter Landon in his Algol 60 used functional composition to model semicolon. Semicolon can be thought of as a stable state transforming operator that threads the state of the machine throughout a program. And it's some pretty big words, but basically this is the first time we explicitly say in a kind of monad tutorial, you could put it as one of the first monad tutorials, where you're stating actually the point of monads is to overload the semicolon, which I think is pretty cool. In April 1990, we're actually getting closer to, actually getting the name monad when Haskell is born. This is the release date of the version 1.0 report, the Haskell report, which sets out to be basically a small specification of the Haskell language. In this version 1.0 report, there were no monads yet. In fact, it tried to be purely functional as well and be a lazy language. And the way they did that before monads was via streams. So you had an incoming stream of responses and an outcoming stream of requests, which is slightly mixed up, but if you think about the runtime, then getting requests and putting out responses, that makes sense. So yeah, your program is the opposite of the runtime, therefore it gets responses and puts out requests. It's kind of weird, but that's how it worked. And it was pretty annoying, even for the time. They put then out a simpler version, which used continuation style effects. And continuation style in functional programming means basically the same as callbacks in imperative programming. So what you do is, whenever you call a function that has an effect, you need to pass down two functions, one for if it succeeds, one for if it fails, for every kind of I/O interaction. That is really annoying. In fact, this is usually called callback hell. If you have to do everything with nested callbacks, that's really bad, and they were really annoyed. And it took a long time. Only in May 1996, 6 years later, Haskell first added monads in the version 1.3 of the Haskell report. Of course, there were experiments with this before that and papers about it and everything. But version 1.3 in 1996 is the first that officially has monads in Haskell. And these monads are, basically like the promises we looked at in JavaScript that are a solution for callback hell in JavaScript, are the solution for callback hell in Haskell. And this makes everything a lot easier. And Haskell also adds something very interesting called do notation. Do notation is a special syntax for working with these monads in a more easy way. The way this works is basically you have a syntax where you can just chain statements after another, like in a normal language, without having to write .then every time. I mean, in Haskell, it would be a weird operator anyways, and they call it bind and not then, but doesn't matter. Concept is the same. They have a special syntax to get rid of the having to write .then or something like this every time. And then we start spreading the monads from Haskell into more languages. As an example, for example, I can take F#. F# released in 2005, like a lot of the other ML languages, uses a lot of monads, but won't ever call them monads. If you look through the entire F# documentation, I think you won't find the word. In 2007, also interesting, C# adds LINQ, which I've mentioned previously, which is for constructing SQL queries or list comprehensions and so on in a very monadic style. In fact, the creator of C#, Anders Hölzberg, said about this. I think it's a great example of a practical application of functional programming. You can happily use it and never even know that you're doing functional programming or that there are functional programming principles powering it underneath. This is from an interesting interview in the books Masterminds of Programming. And even in this interview, he never mentions the word monad. He doesn't do it. He also doesn't mention laziness or any of the other principles that drive LINQ. So you are just left with this vague functional programming principles without ever explaining them, and monads becoming more mainstream, while the word monad is associated with weird languages like Haskell that nobody uses. So it's considered to be a weird thing, even though people are already using it in mainstream and pretty early on. This gets even more interesting with F#, which F# after a while needs to handle asynchronous programming. And to handle asynchronous programming, they come up with what they call computation expressions. Computation expressions are very much based on Haskell's do notation. They are very strictly a way of writing monadic code, the sequences of monadic binds, or then function calls, in a way that looks more normal. The crucial difference to do notation is that do notation looks very different than normal Haskell code. You have the syntactic difference between do notation and normal Haskell code clearly represents the semantic difference. In F#, the crucial point is that it doesn't. It looks almost like normal F# code. You just write in the beginning, basically here starts my computation expression, and then you go. Writing code that looks almost like normal sequential imperative code, but uses monads underneath without ever calling them monads, of course. It's still a pretty complicated system, but you can overload it, you can use it in whatever way, and it gets simplified a lot by C#. C# takes this model, simplifies it, that allows only concurrency and not any kind of other monads, and calls it async await. Now you have a small little await keyword. You just write await in front of your stuff. You need to declare your functions to be async to be able to use it. But once you've done this, you can just bind away your stuff. You can do .then basically instead of .map on your function by just writing await. And your code looks entirely normal. Nobody notices anything weird going on. And you basically have do notation that is so well hidden in the language Nobody even notices. JavaScript, of course, then adopts that async await, makes it even simpler because JavaScript promises are simpler than C#'s tasks, which results in a very simple way of doing concurrency. And this very simple way of doing concurrency has since been adopted by lots of other languages, which just means that's one of the ways we are ending up with there being people who don't know the word monad using monads, which is fine, right? The pattern monad existed before the name monad was applied to it. It's fine. But still, these are sometimes the same people who are like, monads, I don't know what those are. That sounds weird, and weird functional stuff. I don't know. So I think that's one way of looking at how we got here, by the way. I'm kind of cherry-picked these examples. We could have gone through result types and then looking at how Rust does error handling, for example, or we could have looked at list comprehensions or any other kind of monadic structure. It's kind of the same deal. People don't want to punish their users by having to learn about monads and weird stuff, so they just give them monads without calling them monads. Now, in the title of this talk, the second part, I hope everyone is now convinced that monads are everywhere. The second part was, maybe that's bad. That has a question mark after it. I'm not as convinced of this statement. But I think we have to discuss how maybe monads have downsides as well. Like usually in these kinds of talks, they only talk about how monads are amazing, and you should learn them, and you should study category theory, something like that. But I feel like we should look at problems that arise from using monads. For example, if we go back to our example from the result type, which was, the best monad we had so far, what if these have different error types? Right? Like I have this error type left generic, I could place in a string or whatever, that has to be the same for these. I cannot actually do .then and change the error type. I mean, you can feel free to try to implement it, it won't work. You won't do it in a same type safe way. Because fundamentally, if it then failed, I wouldn't know, is it the error type from domain from email address, or is it the error type from TLD from domain? Which means I have to either get them to use the same error type, or I have to compose the error types. What this inherently means is that I cannot be very specific about the error as I'm doing. In fact, I want to look at the Rust official documentation on how to do good error types. Rust allows us to define our own error types. Of course, you can then put it generically into a monad, which they won't mention. In general, a good error type represents different errors with the same type. That sounds really bad, honestly. I mean, you have to do it when you use monads, but that's the opposite of having a specific error message telling you what's going on. You then have to put that error message into a string into your type, or some kind of value distinction. So you need to do pattern matching at runtime to get out what actually went wrong, instead of being able to deduce at compile time what actually failed. But the reason I was using monads is to be very specific about my errors, so that doesn't actually solve the problem that I had with exceptions. The next one is presents nice error messages. That makes sense, perfect. Then the third one is easy to compare with other types. Again, I kind of only need this if I need to compare different errors from different angles. Yeah, that shouldn't really be that necessary, right? Can it hold information about the error? Why is this point number 4 that should be the most crucial one, right? What are you going to do with an error type that doesn't have information about the error? And then 5 composes well with other errors, which is just the same thing again. I need to manually merge it with other error types, because if I want to do monadic error handling, they need to all be the same error type, because monads can't really distinguish that well. And therefore, of the 5 advice points, 3 of them are that you should do bad stuff, that you have to work around the limitations of monads when you do your error handling. And 2 of them are common sense. So that looks kind of bad. I'm going a bit hard here. I actually think this kind of error handling is decent, but there are downsides to this, and I think we should address them. There are some other issues as well. For example, the pretty famous blog post, "What color is your function?" that complains about JavaScript promises. JavaScript promises are monads, so it actually complains about monads. If you have more monads, it actually gets worse. You get more function colors. Then describe individual effects. So, like, again, if I want to have I/O effects in some way, say write to a file or write to some server address somewhere, I would like to be very specific. But monads don't work that great with being very specific. They work very simply if you have the same effect always that you can chain. Therefore, in Haskell, for example, you're usually using the I/O monad for any kind of I/O, which means I can, like, the advantage of using this cool effect system is I can look at a function and go, this does I/O, this doesn't do I/O. That's very cool, but I would really like to know what kind of I/O. And being more specific here would be, in my opinion, very, very useful. With Haskell, that's hard to do. You can, of course, put in the manual label, but that's annoying. And you get really complicated type signatures. If you're not a fan of having type signatures everywhere, monads really aren't for you. If you've ever used complicated monadic structures in a dynamically typed language, you know that is absolute pain because you need to keep track of it in your mind, so you're not getting out of there at all. Let's look at how we could solve these issues. And one way is just to go all in on doing the Haskell way. Let's say we're doing type level programming. We're saying, okay, the issues with weird type annotations is annoying, but we don't care about that issue at all. We're trying to solve the other issues by making the types everything, making the types signatures hold as much information as possible. And Haskell has a cool solution called monad transformers. Monad transformers allow you basically to combine different monads together. Instead of having all these separate monads and then you need to implement manually a new monad, a monad transformer is basically a way to generate a new monad from an old monad. So you can have, for example, a result monad transformer, which is a monad transformer that encompasses the concept of results, so it might fail, and say an asynchronous monad, which just says this stuff happens concurrently or in the background, and I can use the result monad transformer on the asynchronous monad, combine them, and then I have something that is asynchronous and might fail. That's cool. That's really impressive. Well done, Haskell. It's also super difficult. I'm not even going to show you a code example because I think it's kind of hard. And yeah, it makes obviously the stuff even harder. But you can even learn more from Haskell because there's one standard syntax for handling all kinds of monads. That is very useful. For example, if you program in Rust, you might notice the super useful exclamation mark operator that basically gets rid of a result monad. I always want to bind this away and continue with my operation. And if this fails, then I'm returning an error. So you have the exclamation mark operator. Cool. And then for concurrency, you have .await, which is a different operator that conceptually kind of does the same thing. But since we're not talking about monads, not teaching people about monads because they're kind of weird, we're adding more and more syntaxes, which are basically all do notation at the end of the day. In fact, Idris uses the same exclamation mark operator to get rid of results, but also all other monads, which I think is kind of useful. So what you can absolutely go do, if you want to after this talk, is learn Haskell, go in full on the Haskell way, and that's absolutely valid. There are still some downsides. The type annotations are getting more and more complicated by the second. At this point, you're just having like this big of a type just to specify what a function does. And it's kind of hard to understand. Like usually newcomers coming to like languages like JavaScript already confused by async await. It's not the easiest pattern. Doing this for everything everywhere in a way that is composable is and like abstract, obviously it's more difficult. That doesn't mean that it's necessarily bad. So if you want to do Haskell, completely fine. But what if we could imagine like the best possible outcome of this, right? What if we could make a wish list that goes basically all about how we could track effects the best way. And I'm just going to start making up some things that I would like to have. I would like to be able to ignore most effect handling, especially I/O if I don't want to. I just want to allow everything and run my script and be fine with it. That kind of works in Haskell if you just put I/O everywhere, but it's a bit silly, but it works. I also want to be very specific. That is going to be harder in Haskell. I want to be able to pinpoint down specifics. In fact, in almost every language, I think it would be insanely useful if I could check a function and see, is this going to read from disk? Whenever you have a high performance language, you're even going to ask, is this going to allocate heap memory? A lot of people in high performance contexts have rules within this nested loop, you cannot allocate any kind of memory. But there's no way to check this in any language that I'm known of that is mainstream in any way, which means you have to do manual work, manual rules, manual code review to apply this. It would be really nice to just be able to check that. To make this kind of useful, you would need to be generic over the effect, which means if I have something like a list.map, which usually takes a pure function as a parameter, but sometimes I would really like print a debug log from in there or something like this. I would like to be able to annotate the function that I'm mapping with some kind of effect, and then the list.map would have that same effect, which means list.map, which would have some kind of generic effect depending on what function I pass to it. That is obviously a little bit more complicated, but I would like to have it. And in fact, I would like to have really cool tooling. I would like to be able to hover over a list.map in my code and see this is going to read files from disk. It might fail. It might fail specifically only with the following errors: file not found, or you do not have access. Then I know exactly how to handle it. I know exactly what it does. I also know inside of a list.map, I probably don't want to read from disk because I don't want to do that like in a loop. I maybe want to use a different looping construct. But I know specifically what's going on, and that would be really, really useful. Even if you don't limit yourself in any way, having this, I think, is an editor tooling I think everybody would like. Like even if you're a C programmer, you would like to have this. And to make this at all possible, we need to be able to compose different effects automatically. So if I have here a function C defined that calls both function A and function B, and A and B have different effects, C needs to have a new effect, which is basically doing the effects of A and doing the effects of B. And this needs to be automatic. I don't want to write this down every time as a way of creating new effects. Otherwise, my tooling will be super annoying and I'll have to list everything every time. Create new types, use new monad transformers, whatever. And I'm here using the plus symbol, which obviously isn't the proper mathematical way, but I think it gets the point across. And obviously when I'm doing this, the functional order shouldn't matter. Like if I'm calling A of B of X or B of A of X or any of this, the order shouldn't change anything, right? It should be the same effect. If I have a function that can read to disk and read from memory, or read from memory and read from disk or something bizarre, there shouldn't be a difference there, because otherwise it's going to be really difficult, especially when you then combine these effects again. And then there's an obvious one. I want to have pure functions, and pure functions don't add new effects. If I call two pure functions, that is still a pure function. If I call pure function one effect, I just have that effect. That seems common sense to me. Now, the last two ones I can write down in a different way, right? I can call this commutative, or I could call this, the other one, there is a neutral element with regards to combining different effects. Now, don't think about it too hard, but the point I'm getting is, I'm writing my wish list, and the more I'm thinking about the details of my wish list, the more it sounds like axioms of mathematical nature of some sorts. And in fact, this kind of sounds like algebra. In fact, if we make up more of these rules, we end up with an algebraic structure, and that is like too difficult for me, but like there are mathematicians who went all the way, calculated this through, and came up with this actually results in a nice algebraic structure. And so we have an algebra of doing different effects, of handling these effects, and of defining these effects. This is called algebraic effects. So yeah, we're going to talk about algebraic effects now, which are the opposition to monads, basically. Originally, they were just implemented as thought of as a way to improve monads. I believe in 2003, so quite a while ago already, people noticed the same issues I did about monads not really composing. Could we make automatic rules to compose the monads for us, because we don't want to write the monad transformers ourselves? Nowadays, people don't even talk about monads at all anymore when they talk about algebraic effects. They basically, you don't, as a user, have to think about monads in any way when using modern-day algebraic effects. The problem is they cannot be easily used in existing languages. Monads, I just did implement in TypeScript and took like 20 minutes to get like an optional monad done. It's not hard. Algebraic effects, not so much. It's actually a lot of work. In fact, there aren't any production-ready languages right now. So if you want to try algebraic effects, you can use only alpha software. OCaml is the most best-known and stable language, which in its most recent alpha release of this year includes a somewhat limited form of algebraic effects. But it's an alpha release. It's not really practically usable. But hopefully, maybe sometime next year it might be practically usable. Then there's also Cocoa, which is mostly a research language, and as a research language has some downsides. But they're moving towards making it more practical, so maybe it will work. Then there's Unison. Unison is meant to be a very practical language, but it's still a very early release. It's a super young language, the youngest of the three. So I wouldn't use none of them in production yet, but all of them show really interesting promise. And honestly, one of the biggest features is that it's just so much simpler to look at than monad transformers. Monad transformers, in theory, have the same power as algebraic effects. Like I've seen a very complicated mathematical paper that I didn't understand fully, but the conclusion was they can prove that you can take any kind of algebraic effect and do it as a monad transformer. But obviously that misses kind of the point that algebraic effects are just so much nicer to use for you as a programmer. But how could this possibly be implemented? I mean, we're having an insane wish list. How would we get there even? And I'm not even going to show you fully how we get there, and you can figure that out yourself. But I have some pointers where we start. Namely, we can go back to the beginning of the presentation where I said exceptions aren't that great. We could just make exceptions better, a lot better. First of all, we can declare what function can throw. Like you would do that in Swift, for example, where you just say this function throws or this function throws, so you can see this function might fail, this function might not fail. You can hover over it in your editor, you can see it. Then we can go more specific. We can do what Java does or tries to do, that you list specifically what exceptions you might fail with. I hover over my function, I can see this is a long list of extremely long names of Java exceptions that very specifically tell me what's going on. Then we would need a more flexible type system so that I don't actually have to do what Java does, namely write down the list of exceptions every time. That's really annoying. I would want to be able to group them together, say, here's my bundle of these 5 exceptions that come together, and so on, to write these down a lot faster, then allow the generics over it, because that was part of my wish list, allow inferring these so that I can write shorter code and just look at the result of it, and have editor tooling around this stuff, which would be really nice. To make this all really good, you would have to actually implement a pretty complicated type system, which is fairly different from the type systems you would see in most languages. Like in most functional languages, a type is, like a function is just from some parameter to some parameter, but now I need to also add the effect that this is doing, which unlike monads, where it's just the return type, would have to be a different kind of annotation. And then there's an even more insane feature. And I think like a lot of people who are beginning programming, learning about exceptions, think about this and then get told that it's impossible. Imagine you throw your code, you throw something in your code, something has failed, you go back into your try catch field, you're in the catch part, and then you figure out actually there's a way to make this still work. Like you couldn't find the value, but actually I can supplant it, like give you this value. Meaning after it has failed, I want to continue the function that has failed, but with some kind of input or parameter, or after changing something. Which means I want to go back to the function that has just exited and continue it. That sounds fairly easy, but if you think about it, if you have a normal call stack, that is basically impossible, because we're writing the call stack, then we're jumping back up, then we're writing again to the call stack, and then I'm jumping back down, but that position down doesn't exist anymore. I've overwritten part of the call stack already. If you want to do this with a classical call stack, you would have to make a snapshot of the call stack and restore it at a later point in time. And that sounds pretty insane. Or you would have to not use a call stack for your function calls, which sounds like a lot of work for most languages. So implementing this in C is probably not going to happen anytime soon. But in fact, there is a library in C for having these kinds of algebraic effects. Of course, it's fairly limited and uses a lot of preprocessor macros, and it does in fact override the stack manually, which to me, that's insane, and I haven't looked at how it's implemented, but that's amazing, by the same person who created the Cocoa programming language, by the way. So that is possible with a lot of effort, but also that library I would not call production ready in any way, shape or form. So, which concludes with all of these things make it really hard to implement. You need to change your type system, probably you need to add syntax, probably change semantics of some functions, and additionally, you need to change your runtime completely. That's a lot of work. Hence, there isn't any kind of algebraic effects language that is practically usable, even though it was invented in 2003. So monads have developed a lot faster simply because they are super easy to implement. And overall, that's where I want to end. And I want to give you, so what I tried with this presentation is to give you a fairly broad overview of this topic. So I missed a lot of the details. Of course, because I was talking about algebraic effects, I was talking about monads, I had to explain all of this and give you some historical context. I really recommend you, after this talk, to read more about monadic effects and read more about algebraic effects, because they are all super interesting. But that's it for my talk. Are there any questions?
First, thank you very much, Till. Very interesting talk.
Thank you.
Yes. How come you come into this?
Well,
you stumbled upon the paper and then you started to.
I've read a couple of papers, but and part of it was using monads and being annoyed by them, especially in languages like F#. That's also what was mentioned so many times. It does become kind of annoying. So that was part of the background.
Yeah.
And I read about the Coca language and I read about the Unison language. And I was just very interested in how they're doing things because it was such a different approach. And I think it's really hard to understand what algebraic effects are and how they work because there are way fewer tutorials available.
Oh, yeah.
There are some really nice ones, but not nearly as much. And obviously, with this presentation, you also don't know how they work, right? I just scratched the surface.
No, yeah, absolutely.
And I think they are very interesting. I also think monads are very interesting, but very misunderstood in mainstream worlds. So like, obviously some Haskell people really love them, but everyone else is kind of like, I don't know what that is, and that is scary. And I feel like I really wanted to give someone the overview because I didn't feel like there was any place where that overview existed yet. The connection between where monads are coming from. So obviously people know this if they're really in this field, but outside of some really weird functional programming languages, nobody cares about this.
True.
But as monads have shown, even if nobody cares, it might have an effect. In fact, what I think is really interesting, some of the developers working on React, the JavaScript framework, have started saying that some of the features were inspired by algebraic effects. Which is really interesting, right? Like monads sneaking their way in, algebraic effects are already starting to sneak themselves in some limited forms.
Yep.
So that might go somewhere.
We have a question. What is the language of the future?
I don't know. Maybe it will have algebraic effects.
Yeah.
I don't know. I mean, of the ones that are listed here, Unison is definitely the most futuristic. So if somebody wants to look into a very different programming language, that would be the one.
Can you Google it, or do you have like links to some kind of tutorial or Git or something?
You can Google it.
Okay, and then you find it. Yeah, good.
Yes.
Good. And then people are giving shout-outs like a good and very interesting talk, and I totally agree. It was super interesting.
Nice.
Yes, when you sent me this title and overview, I was like, yeah, it's gonna be interesting, but this was super interesting.
Great, thank
you. Yes, also love your like history. So you looked into different languages.
Yes.
Yes. Have you? How far have you? You talked a bit about Algol. Have you looked into?
I haven't practically programmed Algol, but I've always been interested by this. And when I set out to write this, obviously I didn't meant to mention Algol as much as I did. Whenever I did something, I kind of stumbled upon it again, which I thought was interesting because it's kind of the beginning of this, like a lot of what modern day code is.
Yes,
and I think it's very fascinating. And obviously I looked at it before. I think it's very fascinating.
Yeah. What more languages have you looked into? We talked a bit before we started here. We talked a bit what you're programming now, but I mean, have you stumbled upon other languages?
Yeah. I mean, I really enjoy experimenting with programming languages. At some point, I started even writing a blog about experimenting with programming languages, but I didn't get very far. I stopped at like 3 of these blog posts. But I feel like there's a lot of interesting stuff going on, especially when you do further stuff. I mean, currently I'm working with C#. I've worked in the past with F#, Elm, C++, TypeScript, all these kinds of languages. I think there are some very interesting experimental languages. For example, QBML is a language that like no one has ever heard of.
No, me neither. What is it?
It is about subtype inference. So that is the idea that imagine you have an if-else in an ML-like language, and both of these return something slightly different, right? Then in an ML-like language, where you're doing unification of the types. I mean, it will scream at you, these types cannot be unified, right? The if and the else return something different. What subtype inference gives you is by unification. It basically gives you then a sum type that says it is either this or this, which really cool if you have both parts returning a record and both records having a common field. You can just access that field because you know it's going to exist whether you're an if or an else. You know they're different types, but you can access the common part. And that, to me, when I first saw this, I felt like that's kind of insane magic. It allows you to write really different code. And there has been like one PhD thesis on how to implement this. And QBML is very much just an experimental language to show that it's actually possible. Not at all practically useful. But I think that's like really cool stuff.
Again, thank you very much, Till. Thank you. I don't have any more questions, but people are shy to shout out like cool. Yeah. We'll try to post as many links as possible below the presentation when we publish it later on YouTube.
Awesome.
So you can throw in all the links.
Yes.
If people are interested. Yes.
Perfect.